Hello everyone, my name is Manli Zhu. Today I'm going to present the work Interpreting Deep Learning-Based Cerebral Palsy Prediction with Channel Attention. Cerebral palsy is one of the most common childhood neurodevelopmental disorders in the United States. It is estimated that between 3 to 10 out of 1,000 children develop some form of CP, depending on gestational age at birth. Therefore, early diagnosis of CP is essential as it leads to taking the treatment as early as possible for preventing bigger health issues. Traditional automated general movement assessment-based methods for CP prediction are time-consuming and often require human interference because a threshold has to be defined manually for the final prediction. In recent years, deep learning has become a popular technology in medical diagnosis thanks to its high capacity. However, many existing works for CP prediction still heavily rely on handcrafted features, which means they require considerable domain expertise and may not be transferable to another domain. Notice that these methods are also not interpretable by humans. However, interpretation is very important in deep learning-based disease diagnosis systems as it allows physicians and regulators to have the confidence on the diagnostic result. In this paper, an interpretable deep learning framework is designed for CP prediction. Our main contributions are that we present a channel attention module to interpret the deep learning system. We propose a novel attention loss function to facilitate better human understanding. And we also visualize the joint's attention values in a human understandable way for the interpretation. Here, we introduce our overall framework. The input of the network is a temporal sequence of joint positions represented as a tensor, which is also a multi-dimensional matrix. It is then fed into a channel attention module, including squeeze and excitation blocks. Unlike many other works that model the coordination dimension as channels, we model the joint dimension as channels. In this way, the importance of each joint is represented by its respective channel attention value. This channel attention module allows the system to tell us which joints are important for its diagnostic decision. We also develop an attention loss to minimize the number of attended features to facilitate better human understanding. The attention value is then multiplied with the input feature, forming an attended feature tensor. Such a tensor is fed into 5 2D convolutional layers to further extract the high-level information. Finally, a fully connected layer and a softmax layer are applied to perform the classification. Our final loss function is formed by the commonly used cross-entropy loss, our proposed attention loss, and the L2 regularization term. Our attention loss is implemented by summing up the attention values of all joints together, such that it can minimize the number of attended joints. The L2 regularization is used to avoid overfitting. Moreover, in order to reduce the influence of data bias in the used dataset, we also apply this class balancing weight function in the cross entropy loss. We verify our model on the moving infants in RGBD synthetic dataset, short for mini RGBD. All infants in the dataset are a half-year-old, and it includes 12 video sequences in total. Each video sequence was annotated either normal or abnormal by an independent medical expert. Finally, 8 of 12 sequences were labeled as abnormal, and 4 were labeled as normal. As mentioned before, we can see that there's a data bias in this dataset. Here are the quantitative evaluation. We first compare the classification accuracy between our method and other baseline methods. We can see that our full system achieves the same state-of-the-art prediction accuracy. And even without the attention module, it still can achieve the same accuracy. Well, this is because our attention module is designed for interpreting the network instead of improving the accuracy. So to further improve the accuracy, we may consider other designs. This is the result of the influence of the attention loss in our framework. We can see that the loss term effectively reduced the average per joint attention values, and the average number of joints with high attention values is also reduced. We can see that the loss term allows the results to be more easily understood by humans while maintaining the same prediction accuracy. Here, we present the visualization results. We first visualize the attention values of all joints across 12 validations. From the median lines of the box plot, we can see that the joints left thigh, right hand, thoracic spine, right shoulder, and right upper arm have the highest attention values in almost all the cross validations. Notice that most of these joints are located in the upper body, including those on the arms and the shoulders. This aligns with the results reported in previous works that the features extracted from the arms are more discriminative and resulted in higher accuracy. We also visualize the joint attention values distribution in 2 cross validations with a normal sample and an abnormal sample. It can be seen that the example motions from different classes resulted in different sets of attention values. This highlights the network has different focuses on the body joints to differentiate motions from the 2 classes. To conclude, we propose an interpretable deep learning framework with channel attention for cerebral palsy prediction. We propose an attention loss for minimizing the number of attended joints for better human understanding and analysis. We visualize the attention values of joints for interpreting the proposed deep learning framework. That's all. Thank you.